Hello everyone. So today I'm going to start working on a spherical grid system for the planet generation system that I'm working on. So the reason that I wanted to work on this is because I am planning to implement a LOD system for the planet generation where when I go closer to certain tile on the sphere, it should be rendered in higher details like a typical LOD system. And to implement that, I need a way to determine something like a tile, a landscape tile, but on a spherical surface. So that's why I need to figure out this part. So this is just a demonstration of how I am going about determining these tiled areas. So I haven't still implemented the underlying actual grid system where the actors and everything is associated with the grid yet. This is just the starting point. We are just going to figure out the math behind, like how can we divide the surface area of a sphere toward tile. They are not exactly the same size. The size changes as I go closer to this North Pole and South Pole, but still we have some kind of a tiled surface area that we can use to implement a LOD system. So that's the direction we are heading. Alright, so let's see how to do this today. And before we get started, I'd like to remind you, you can download the project files of this project and all other thousands of projects that I have done in my channel. To the date, there are 1800 videos, so for each video, project file is accessible. For the membership of the Patreon page, you can download anything without a limit. Feel free to check it out. I'll leave the link in description below. Okay, so before we start implementing the grid system, I'd like to explain few things in a simpler way rather than going in a pure mathematical approach. So let's just see how the angles or rotation works for a scene component inside an actor. So here let me add a scene component and I'll call it, what should I call it, rotation root. So this is for demonstration purposes, so it's in the center, and under this I'll add the arrow component so that you can see it, but it's not large enough, so I'll make it not yet. Here this scale worked is 20,000. Okay, so now let's create a custom event, rotate test, let's call it, and then here let me drag and drop, and I'll add a rotation offset, add relative rotation. Yeah, let's try this. So let's change, if I split this, you can see roll, page and yaw. Let's change the yaw 10 at a time. Compile. Now go here. Where is the arrow? Okay, arrow is in that side. Now I'll make this event enable call in editor so that I can press that in the editor right here. Now we have rotation test. So if I press it, now you see as I press it, it goes around the planet. Now also let me get relative rotation and print it so that you can see how the rotation changes. Let's keep it for 10 seconds. so we have enough time to observe. It's not appearing here, okay, but it should be appearing here. Yeah, see. Let me reset the rotation to 0 and start from the beginning. Okay, now again rotation 10. Pay attention here how the rotation changes. Here yaw is 10, 20. Yaw means y in the middle, so that component is responsible for rotating this arrow around. So note that once it goes to 170, then it doesn't go to 180, instead it goes to minus 180, and then it goes from, it start going down in minus values. Here 170 minus, 160 minus, and it goes until it becomes 0, which is the starting point. So it changes from 0 to 180 and then minus 180 to 0 from the negative side. Okay, similarly, remember that. Now let's change pitch 10 at a time. Now here you see it changes in that direction, and here it changes from, here you see P or pitch is changing from 10, 20, 30, so it goes to 90, and then it starts reducing. No. So here what happens is it fluctuates in between 80 and 90, but also note that the roll is changing from, sorry, yaw is changing from 0 to 180. So this is important. If I first start with 180 for yaw, let me set it back to 0 and make it 180. Now if I start increasing here, note what happens. Now again it changes and goes to up, and again the same thing happens. But here note that it comes from this side to here, and pitch is changing from 0 to 90 with with 180 for yaw. Similarly, let me make this minus 10 and see what happens. Okay, now it's minus 10, it goes back and it goes down until it reaches down and start fluctuating here. So here it changes from, yeah, so anyway what we can know is pitch is changing from minus 90 to plus 90, so that's the range of pitch, and the yaw's range is 0 to 180, then minus 180 to 0 from the other side. Alright, now with that knowledge, here let's add a new function, draw spherical grid. Okay, so we know that we're gonna need two for loops. So for loop starts from 0, last index. I'll promote this to a local variable, let's call it grid size, and I'll make it 10, and then another for loop. Here also I'll use the same grid size. So now I'll consider this as the yaw change. So this is changing from 0 to grid size, so that means I need it to change from 0 to 100 and, oh wait, not 0, it should change from minus 180 to plus 180. So here I'll change this grid size. I'll multiply this grid size with -1 and I'll use it as the first index. And here also first index should be starting from minus grid size to plus grid size. Okay, now this is the yaw change, so that should be changing from -180 to 180, but here we are using 10, so ideally we should be multiplying this with 18 to get 180 and -180. But if I decide to change the grid size, then also it should automatically adjust. Therefore I think I should how should I do this? Divide, convert this to a float, 180, and divide by this value, grid size. Okay, and then multiply it here, right? Make sure that you are not using 0 for the grid size. And for the pitch, I calculate pitch using this, and here it should be changing from -90 to +90. So same as here, but I should divide 90 by the grid size and multiply like this. Alright, now I will set the relative rotation of this rotation root. As I said, I'm not going to completely mathematically derive this. I'm just going to use a lazy approach. Here I'm going to set yaw from this and pitch from this. Okay, why am I getting error here? Okay, so right now it's not enough to set the rotation, we need to visualize this. So for that I'll add a line, add a draw line. Let's draw a line. No, let's draw a debug line. Draw debug line. A starting point is actor location because that is the center of the planet. So get actor location, and then line end would be, I can get this rotation root and get forward vector, and I can get a point along this forward vector outside the planet radius. So I can multiply this with the planet radius, but the radius is in kilometers. So here let's multiply the radius with, it's in kilometers, multiply it with 1000, so we get meters, and another 100 we get centimeters, which is unreal units. And I'll promote this to a local variable, I'll call it R, and I'll make this, I'll multiply this with 1.1, so we get a point a bit outside the radius of the planet, and then add it to this. That's the end. Line color, let's use something like this, more visible, duration 10 seconds, thickness, we need a bigger thickness because we are working on planetary scale, so this might work. And compile. One more thing, I'll make this to a spherical planet, a spherical grid, call in editor, so I can draw it in the editor here. Yeah, see, now we have a set of lines like this, which is the basic points that we can use to draw a grid. I have made a mistake. This part should go to yaw and this part should go to pitch, because here is 180, here is 90. So that's why we didn't get as much as lines that I expected. Right, now this is correct. Okay, and we no longer need this arrow, so let me delete that. Okay, next step is drawing the grid. So for that we need to save these points that we generate, especially this point that we generate, into some array or something. But I think in order to draw boxes, I don't think saving directly into an array might be convenient. So rather than that, I think saving it into maybe a map would be more suitable. So here grid, I'll call it grid, yeah, just grid, and I'll change this to int point, and then I'll change this to a map, and the map as the value will hold a vector like this. Now we can, well, here since I make it a global variable, I should clear it before I try to recreate the grid, just in case if we have anything in the previous run. Okay, and then to the grid I'll add this generated point, but as the key we can use this index values. So here let's make an endpoint, and x would be coming from here, y would be coming from here, like this. Now after adding all these points here, now we can draw the grid. So that means here, after this is completed, I would need another 2 for loops. So let me duplicate the 2 for loops here. Now the starting point, but same as before, starting point would be grid size -1. Wait, didn't select this, and Control D. Okay, so that's the starting point for both for loops. And the last index, instead of going for the grid size, I'll go for grid size -1. It's already minus, so just 1. The reason is I'm gonna need 2 points to draw a line, so you'll understand. So that's why basically. So here now, from this grid we have to find 2 points. We have to find 2 points to draw a line. So this x, so in would be coming from here and y would be coming from here, and then but in I'm gonna draw a line, so like this, draw debug line. So this would be the starting position, and the end position should be the next point, maybe along the latitude. So we need another one of these nodes, split, so x will remain same, y, we will need to add 1. Let me add a reroute node here. For while, I'll add 1 so that we can get the next point along the latitude. Sorry, it should go here, and that should be the next point. I'll make the line red, duration maybe 10 seconds, and thickness I'll use the 5000 because that worked before. Right, compile, let's draw. See, okay, now we have the line along the latitude. For the longitude, we can, so a starting point could be the same, like this point. This is the horizontal line that now we are drawing, and the next point should be the next point along the longitude. So that would mean we need to add 1 to x and keep y the same. So use the same y value, x incremented by 1, like this. Compile and draw. Something is wrong. What did we miss here? Let me make this public, and here let's add a branch just to, and only if this is true let's draw the line, otherwise let's print so that we can see which point is missing. I'll print x, because the reason I do this is sometimes when we have a missing point, it draws to 0. It go I think this returns 0. Maybe that's what happens here. And y, let's see. Okay, so these are the points that were missing. Why are they missing? But now you see the grid draws correctly. See? Now we have a perfect grid, though we have a problem in our code. And we can also inspect the values of the grid, starting from -10. Okay, so the first missing value is -9, -10. But I have the -9 and -10 here. Oh, sorry, I should have, okay, this is a mistake. This is not the final point. I should have connected this complete node. Sorry about that. Now it should work without having this branch because I'm sure we have all the values we need. Okay, now let's test. Draw a spherical grid. Yeah, this is correct. Alright, so yeah, now we have some idea how we might implement a sphere grid system. So next time let's try to get started with the LOD system now that we figure out the grid part. And I don't think that's gonna be easy, but I will try my best to figure that out. And thanks for watching. Don't forget to like and subscribe, and I'll leave the updated project files here. Thanks for watching. See you in the next episode. Goodbye.